Good. Today, talk about hazards to help with the last two problems in the whole book. But before we do, there was one formula we never talked about, which is you'll need to do problem 5, and it's just very simple. That's why we didn't go over it. It looks very complicated, but it's very simple. And if you're a physics major, I'd probably spend more time on it. But really, from your point of view, it's not as important. I'll just tell you how to use it. So you know the potential, how to get the potential from an E field. Somebody gives you an electric field, you get the potential doing this. You can invert this, do the opposite, to get the electric field from a potential. This is the formula, and where this is an integral, this becomes a derivative. Now, because it's a vector, you got to do every component separately. And then the thing that looks scary is this this symbol. It's a backward 6, which anybody's seen it before? Yeah. So it's called a partial. On all purposes, it's basically like a derivative, a d. Okay, but because v is now more than one variable, it's a function of x, y, and z. We'll use this symbol instead to differentiate, no pun intended, between the two kinds. But you just, from a practical point of view, you're just taking the derivative of v with respect to x. And then to get the y component of the electric field, you take the derivative of v with respect to y, and so forth. Okay, and that's all it means. So let me just do a quick example. Of this. The potential is given by this is units. Let's put the units on the side. 3 xy minus 5 z squared, and then the units will be volt over meters. Okay, and why is it volts over meters squared? Well, because these x and y's have units of meters. So you need to cancel that to get volts out of this. Okay. So just to use this formula, find so it gives you this potential that depends on both x, y, and z. So it's different from the. Okay. Never mind how you make this potential, but just say someone gave you this potential, and you want to know the electric field. So you first find Ex, dV, dx. Okay, and you take the minus sign, take the derivative of this with respect to x, ignoring everything else. So the derivative of this with respect to x is just 3y. The derivative of this with respect to x is 0. It doesn't, right? And then keep the units. Minus 3y. And EY would be, you take the derivative of the potential with respect to Y. And what's the derivative of this with respect to Y? 3x. It's 3x. And then this is going to be 0. Minus 3x meters squared. Then EZ. And what's partial B, partial Z? What's the derivative of this first term with respect to Z? 0. And you get the idea. And then this one, yep, there's Z. And we have 10Z volts per meter squared. And so at the end of the day, we can write out the full vector electric field as being, so the E field is going to be equal to minus 3 y I hat minus 3x j hat plus 10z j hat volts per meter squared. And if another question was what is E at point 2 meters, 3 meters, 1 meter, you just put it in here. So E would be equal, this is X. So you doesn't go in, there's no X component here, X value, but the only value is Y. So you look at here, it's 3. So it's minus 3 times 3 meters I hat. This would be minus 3 times 2 meters, because that's what X is, J hat. And then last is plus, and Z is 1 meter. J hat. Volts per meter squared. And then you just multiply this out. You get minus 9 I hat minus 6 J hat plus 10 K hat. The meters come out, one of the units cancels that, so volt per meter. And that'll be the answer. We're just doing one of the problems in homework requires this, which I quickly went over. You can look in the homework in the video that I'm recording to catch up. But this would be specifically problem 5. The same idea. Here's your potential, and then you use the formula that's on the board to get the electric field. Here they ask for the magnitude. So after you find your EX, EY, EZ, then you take the magnitude and then find the angle. Right? Question? Yeah.
So is there 2, 3, and 1 representing each vector? Like a point at each vector, or just?
It's just a point in space, 2, 3, 1. And the electric field depends on in space. It changes in space. So it has a different value where depending where you are.
How do we know what one?
So you read this as X, Y.
And so to take that angle, do we do like a scalar projection?
Yeah, just like the, so this is just X and Y, so. Yeah, EX,
Yeah.
EY. And then the angle will be the tangent EY.
Okay. Are you gonna have a Z too, or is it?
Not, this problem doesn't have a Z component. And then it actually says the A on that. Let's see. Okay. Okay, but back to the main thing today. It's about capacitance and capacitors. So just to remind you, capacitor is something that the capacitance comes from, you can see capacity, the word capacity is in there, and it's the ability to store charge, okay? So just to remind you, okay, the C is defined as, if I put a potential across something, anything, doesn't matter how much charge had to move to give me that potential or responded to that potential, okay? And the more charge I get, the larger the capacitance. You know, if I put, it took me 1,000 volts to get 1 coulomb to come there, that means it's low capacitance. But it only took a volt to bring a coulomb there, then it's high capacitance, right? And so that's the basic definition. You also think of it as a coulomb per volt, you know, kind of a density thing. How much coulombs do I get per volt? And we did it for a charge sphere. Derive the formula, and it ends up, it just depends on the dimensions, geometry of the object. So for like a charge sphere, it was just R over K. The other one was parallel plates. Okay. And that's, you know, we're assuming that these plates are really big. That means the area is much bigger than the separation. So one side will have charge Q, the other side will charge minus Q. A will be the area. And if we work this out, and we found the capacitance of parallel plates was A epsilon naught D. So it depends on the area. That makes sense. If you make it wider, bigger, you have more places to put charge. And inversely proportional to the separation. That also makes sense because if you decrease the separation, the potential increases, the potential jump increases. Remember the electric field? No, I'm sorry, the potential decreases because there's not that much distance to jump, so it decreases. And since potential decreases and it's on the denominator here, it's going to increase the capacitance. You don't need that much potential. Okay. So problems 6 is just that formula last time for our charge sphere. I forgot to share. So 5 was what we were talking about before. 6 would be a formula for the charge sphere. 7 is this formula right here. Right? If you're given this, what would be the voltage difference? And then, so now we have 8, 9, and 10 would be material about capacitors, which we'll talk about now. Okay, yeah, charge sphere. So you have a sphere plus Q. There's no other spheres. It's all by itself. So you're comparing it to the voltage with infinity, which is 0. So C is just R. This is greatest R over K is the 8.99. Okay, so now we're gonna go into capacitors as we do it in a circuit, and then here in an electric circuit. Okay. So you can see a circuit board. While resistors are pretty much look the same, so the resistors, capacitors take many different forms. This is a capacitor, the one that looks like a battery. That's the capacitor. But these yellow ones are also capacitors, smaller. This is a big capacitor too. I think they're batteries. High amplifiers. Okay, so stop sharing. Capacitor. We're gonna write the symbol that would appear in a circuit diagram as that, and that's because we're taking the parallel plate, making a symbol out of the parallel plate. So this is a symbol for capacitor, and if you put charge on here plus Q, then an equal amount of charge will be on the other side, and it will give you a potential difference of delta V, so that C over Q equals delta V. Or you can solve for delta V. That would be Q over C, or Q would be C times delta V. Okay, so when we're doing circuit analysis, depending on what we're being asked for, we could be using any one of them, which is really just one formula. We don't have to worry anymore about the separation. Once you pick up a capacitor, you read the value, right? It'll be in, remember, the units will be in farads. So a farad is huge. You'll never see that. That'll be like paper. It'll be like garbage can size capacitance. You don't want that. So things will be, the smallest will be picofarads, right? The tiny ones, all the way to typically millifarads. Now that's already the size of your pinky. Okay, So let's talk about a capacitor circuit. Remember what the primary job of a capacitor in a circuit is to, at least in a DC circuit, I'll go back. Stores charge. Have something on the circuit board that it's storing charge. Now, if you go to AC circuits, capacitors have different properties that are used. And we won't get into that now. Okay. Capacitor circuit. Basic circuit is obviously you need some power, source of power. So we're going to hook it up to a battery. The potential of the battery is V0. So this is the symbol for a battery. It also looks like a capacitor symbol, except one side is smaller. And this is to show you that if the longer side, that's always going to be represent plus, the plus side. So a battery has a polarity plus and minus. And then we'll have a switch, right? So that's represented like a door. And then over here, we put our capacitor and then complete the circuit. This capacitor has a value of C, okay? So when the circuit is open, or the switch is open, okay, like it is shown now, these lines are wires, right? They represent wires which are conductors, and conductors, what do we know about conductors? Charge moves freely, and then two, electric field is zero everywhere. Good, right? And so if the electric field is zero everywhere, if this is at potential V naught, then I can move charge along here without any work need to be done. So this is also V naught, okay? So this whole thing is a equipotential line. This whole thing, charges are moving up to here, and they're also at V naught, okay? So I just want to, understand that. Over here, though, there are no charges because it's broken, right? The charge can't go over to here. So these are all at, we'll say, like 0 voltage. Okay? Voltage is relative, so this can all be, remember, be floating. We can be at 100,000 volts, like the guy in the helicopter and stuff. But so we can always choose this to be 0 and this to be something above 0. Okay, so when switch is open, there's nothing on the capacitor, like we're saying. Q would be 0. E, the electric field is 0. And then delta V is 0, okay? No, the voltage difference is positive 0. Now, when we close the switch, what happens? So instead of redrawing this, I'm just gonna erase it. Okay. Bam, you close the switch, you connect this up. What do you think happens? Yeah. Yeah. So charge now, remember it was all plus here. Now there's a way to get out because it doesn't want to be next to each other. It's repelling. So it flows out this way. So everywhere would be charged up, including a capacitor. Okay. So this becomes plus Q. And this entire line here is going to be at U0 potential. You now have plus charges here. They're gonna produce an electric field that points down, right? Because it goes from plus to minus. This electric field will draw negative charges. Okay, so it'll draw negative charges to this side. And so this whole thing will also have negative charges this way. Now we're still calling that zero, okay? Because we can just change the level. So don't think I'm contradicting myself. Negative charge is supposed to be negative both potential, and positive charges is positive. Yeah. Like say say this is negative 10 volts. If I add 10 to everything, then now it's zero. Say this is negative 10 and that's positive 10, right? And the difference is 20. But if I just change it, what really matters is the difference, nothing else. So if I change this to 0, I add 10 to it, and this just becomes 20. Okay. And so the analogy was the guy in the helicopter who fixes the 100,000 volt line. So when he charged up, the whole helicopter is at 100,000 volts, but it didn't wreck the electronics equipment or anything. And that's because it's the potential difference that the electronics worries about, not the potential of the entire circuit. Okay, so to make it easier, we change this to 0, even though we're talking about negative charges. So I want to just make that point clear. Okay. Okay, so when switch is closed, we have plus Q over here, minus Q over there. What's the potential difference now? It's going to be, so we have charge Q, we have an E, right? And we have a delta V that's equal to Q over C. Right? And in this picture, delta V is, if this is V naught and this is 0, that's just equal to V0. So you can actually find Q. The only thing that's not known here, since we know the battery, we know the capacitance, we know Q is going to be C V naught. The last point I want to make sure you understand is the positive charge came up here, it stopped. It can't do anything else. Negative charges came up the other side and met it, and it stopped. Nothing ever actually moved across. And that's why it shows a kind of a break, right? There's no line between these two. So if someone asks you, what's the current? How much current went through? You would say 0. No current ever went through this circuit. Okay. Current actually moved to here, but then it stopped. So there was current in the beginning. So you switched it. It had to go this way. but we don't care. We wait for it until everything settles down. Okay, we haven't talked about current yet, right? So I'm getting a little bit ahead of myself. So we're waiting until everything settles down and then asking what's the final charge. Okay. Okay. So that's one capacitor, one battery. What happens if we put two capacitors together? Then there's actually two ways of putting two capacitors together. The first is from capacitors in parallel. And we'll just draw a circuit again with voltage V. Here, V just put V. And then over here, put one capacitor like before. And C1. Second capacitor. C2. To be a switch. No switch at this time. So we, like I said, we wait till everything's charged up and everything, so we don't need a switch anymore. All right. So what does in parallel mean? Okay. Parallel means over the years, many students have seen many students have difficulty understanding, figuring out what's parallel, and the other one is called series. Okay. So I think I'm trying to develop some rules, but basically you're in parallel if your voltage doesn't change when you if you can ignore the one or the other and your voltage doesn't change. Technically, parallel means they both see the same voltage. And when I say that, students have trouble understanding what that means. But in this picture, if I ignore this one, what voltage is going across C1? What's the battery? So if I ignore this, just pretend it's not there, what voltage does C2 see? Also B. Okay, that's what parallel means. So develop a little phrase. Means same volt. Okay. So parallel means same voltage, but different charge. What does that mean? Well, we're assuming these two capacitors are different values. Because they're different values, their different charges will accumulate. Remember, they're seeing the same voltage. So this one will have plus Q1 accumulate on this plate and plus Q2 on the other side. Now I'm going to ignore the minus charges. I'll imagine it's the Q, the positive. Once you know Q, you know the other side is minus Q. Right? Because this one has lower capacitance, it's not going to bring them have as much charge. So the charge though, is going to be just from that formula we just wrote over here. or the other, no, it's only one formula, Q equals C over V. The C equals Q over V. Rearrange it so Q equals C times V. So this charge would be C1 times V. And then this charge is Q2 is C2 times V. So that's what we know. Now, the battery, the battery doesn't, all it knew is charge moved away from it and did something. It doesn't really know that there were two passengers. They could have been three, they could have been four, they could have been a million. So we can do what's called replace this with what's called an equivalent capacitor. Equivalent capacitor. Okay. Is there a capacitor that when we replace these guys, one capacitor only, that is equivalent to this, meaning the charge that's accumulated here is the same that left the battery in this. Okay, and so we can find out if, actually, because well, we already know that C equivalent. I'm sorry, Q equivalent in the same formula is equal to C equivalent. So we know that. And then our requirement is that Q equivalent, the amount of charge that accumulates here must be the same as the charge that left and found itself over here. So it must be equal to Q1 plus Q2. Okay, conservation of charge. And so that last equation, I'm going to continue it over here by plugging in what those are. So that's going to be C equivalent times V equals C1 times V equals C2 times V. Okay. And you see that the V's all cancel. And the equivalent capacitance is C1 plus C2. So that's a formula. For capacitors in parallel, the equivalent capacitance is just the sum of them. Okay. And so if you can remember two things, phrase, same voltage, different charge, and that their capacitances add, that's all you need to remember for capacitance. Yeah.
This will be the point of making circuits. Like what we're into.
Honestly, it's very boring. Not much, because again, these are DC circuits. But you want to store charge. So you have to imagine. So say one part of your circuit needs 5 volts, but another part needs 10 volts. So you'll have to like kind of do something to bring the voltages to bring it up to 10 here, bring it down to somewhere else, something like that. So just storing charge. Now, when you're going to AC circuits, store charge quickly, but then they get leaked out, and so you do something. These are called like bypass capacitors. They protect the offense. So there was a quick surge of voltage, they'll deplete it right away without putting it on. These are protection capacity. These are for the storage, really, the storage part of the higher voltage. At some point in time, the switches in to store charge, and then it'll switch out to release. So these are kind of like the water tanks around town, you see, right? So sometimes you need charge a little bit, but sometimes you need a lot, so they open up the circuit to let more through. Yeah. Okay. So the second way to combine capacitors is to put them just back to back. Now I think this is the hard one where people can't decide if it's in series or in parallel. So you're doing this. And the way I like to think about it is, can I go through one without going through the other? And I can't, right? There's C1 here. I can't bypass it to get to C2. Over there, I could. In the parallel case, I can go through C1 or I can go to through C2. No problem. So there, and if another way to look at it is I remove one of them, basically I broke the circuit. C2 dies as well. Whereas in the parallel case, if I remove any one of them, the other one's still okay. Okay. So I don't know how you can, if you're having difficulty with seeing this, but in series means, technically it means back to back. So this is connected to the battery. The other end is connected to the other capacitor. And then the other end of the second capacitor is connected to the battery. So that's in series. Okay? It's like a chain going along, like a train. Anyway, the phrase that you should remember here is same charge, different voltage. So once you know that it's not parallel, then it can't be same voltage, so it must be same charge. You switch the two words, same charge, different voltage. Now, why is it same charge? Okay, so remember, charge moves over here, so this becomes plus Q, right? And if plus Q is there, then minus Q must be here. Okay. Well, charge is conserved. If minus Q came here, and this was neutral before, then there must be plus Q on this side. Okay. And then if this is plus Q, it's going to draw minus the same amount on to the other side. So both of them have the same charge. Okay. Now, different voltage. Well, if they have different voltages, different capacitances, C1 and C2, but the same charge, then they must have different voltage, right? So voltage one, you just rearrange that equation again, right? So it's going to be Q over C1. And voltage two will be Q over C2. Right? That one equation, you just have to, the only difficulty is not rearranging it correctly and then getting the wrong answer. That would be the only thing, because it's just it's a very simple equation otherwise to remember. So we can do, we can ask the question like before, is there an equivalent capacitance that will be the same as this circuit? What would it be? So in this case, we have to get what CEQ is, we have to see that, you know, if I'm up here at V, I'm gonna go through a voltage drop. If I jump over here, I'm at some place that's not V anymore, but V minus V1, right? Because there's a voltage drop here. And then I do another voltage drop, V minus V1 minus V2, then I get to 0, right? So that means V is going to be V1 plus V2, okay? Let's see. So for the folks at home here. But yeah, if you add these two voltage drops together, V1 plus V2, you must equal the total drop. Well, V here and here, remember, the battery doesn't know how many capacitors there are. It just knows how much charge left. So in this picture, it'll see the same amount of charge, just like in the other picture, right? It only saw Q coming out. So this side is going to be Q over C equivalent. And then this side would be what we had before, Q over C1, Q over C2. And this time the Q's are the ones that cancel. So the formula for the equivalent capacitance is the reciprocals add, yeah.
Diagram, why isn't this like capacitor like having negative on top and positive on top?
Because of charge conservation, initially it's neutral. It was 0. Initially, when the switch was open, it was 0. And then now you close it up, minus Q went to the top, so plus Q has to go to the bottom. I want to get away from towards the other side.
It becomes like a dipole.
Yeah, yeah. So. Yeah. Okay, so the phrase is same charge, different voltage, and the capacitance, the reciprocals add. That's what how you say it. You add the reciprocal. Now, the general formula is very simple. You keep doing this. So C equivalent, say for parallel, is just C1 plus C2 plus C3 plus to how many capacitors you have in parallel. This is the same thing. It's 1 over C1 plus 1 over C2 plus 1 over C3, all the way to 1 over Cn, how many capacitors you have in series. Okay. That's the completely general formula. Okay, good? Everybody's good? Okay, seems so easy, huh? Okay. So now we'll do a capacitor circuit problem. Now we have to, now is where you put your thinking caps on. There was already one, we did a simple problem was done in the video of reading. Um, the 8 and 9 in the homework are more like this. It's more like this one, whereas 10 is more like the video problem. So we have this capacitor circuit that is a mixture of capacitors that are in parallel and in series. So that's seems to be the hard part, the complication here. Huh? Oh, well, yeah. Well, there's actually 8 parts to this. So there's a lot of things. Well, I'll show you. I'm going to recopy on the board first. So we have the battery. We have C4. C4 is the dangerous one. And then, okay, and we have 1, 2, 3, 4, 5, 6. And then C1 equals C6 equals 3 microfarad. By the way, you don't have to worry. If you're trying to find capacitance and stuff, don't worry writing a 10 to the minus 6 inside. Just keep it micro. C3 equals C5 equals 4 microfarads, and then C2 equals C4 equals 2 microfarads. Okay, so before we kind of go into it, now things look a little different, but I wanted you to understand a certain fact. These wires are equipotential lines, so we can make them smaller or longer. It doesn't matter. Okay, they're still the same potential on this side as that side. So that means you can actually move this, say for this one, up here. You can move it along it as long as you don't cross a node. It's called a node, a meeting point. You can move it like this. So here it might not look that these capacitors are in parallel, but they are. Because if I move it up here, then it looks like that picture I showed you. Parallel. These are what? Series, good. And if I move this like that, then this and this are parallel, good. And then all these guys are parallel. Okay, good. And then the idea is you can replace this whole thing with 1. Okay.
You can move like C2, you can move that to make it
Well, you can move it. Whether it becomes parallel or not depends, but you can definitely move it to like here. And then the combination of these guys and this one, they see the same voltage drop. So they're in parallel. Yeah. Because then that'll be bad. It'll be probably the end of the world, because you're really diverting. This is like charges. It's like a freeway. You're creating a new circuit. Before charges had to go this way, and if I brought this over here, basically it can't go there anymore. I just blocked it. Right? So you're making a new circuit. And when we go into resistors and real circuit analysis, these are places where whatever charges that go this way must equal charges that go out there. So you can't, you'll be violating that rule when you do that. Okay, so the first question is, what is the equivalent capacitance of the capacitor? We want to replace this circuit with one capacitor only. And what is that value? And here we don't have to find a formula. This is the only time you don't have to. I like numbers are okay. You can use numbers. It's also the only time where you can leave out units too, okay, to make the math easier. So that's the only exception. I'll let you have, even though you don't listen to me anyways. But you just put the numbers, okay, and don't worry about the micro. Just call it 3 and 4, 2. So how the way to do this is you don't do it all at once. You do it slowly. Boom, boom, boom. You figure out which one's in series, which one's in parallel. Combine them where you see it can be combined. Okay. So this is the way I like to do it, because otherwise it becomes a mess. Also keep the notation nice and neat, and adopt my notation because it's superior, okay, than anybody else. Okay. So what we're gonna do, things that we see can be combined, that's what we're going to do first. We're going to replace this circuit with another one. Right now, what do you guys can see can clearly be combined? Yeah, so that's what we're gonna combine. C4 is left alone. These guys are combined to be called C35. Okay, so that's my notation. The two become together, they're called C5. And we already said C2 can be moved, so I'm going to go ahead and move it. So that we can go to the next part, next step. C2. And then over here, we have C6. Let's go ahead and move C1 too as well. I don't have to draw it again if nothing changes. Okay, so what's C35? What's C35 numerically? Well, we said it's in series. Yeah, right. And capacitors in series, they're reciprocals add. So it's actually 1 equals 1 C3 1 C. And so this equals 24 plus 5 is 4. So that's 2/4, which is 1/2. 2/4, 1/2. That means C5 equals 2. Remember to invert it, because that's a common mistake to not invert it at the final step. So C35 is equal to 2 microfarads. Okay, now we combine some more.
Capacitance of two larger capacitances, like in series, get a small capacitance.
Yeah, yeah. It's, yep. So when they're in parallel, it increases, but when they're in series, it decreases. Okay, and reason is because it's the same charge, right?
Yeah.
But you basically have a bigger voltage now than before, and charge over voltage capacitance. The voltage increased, so the capacitance decreased. The ability decreased. Yeah, so you can always decrease capacitance by putting more in series, which is counterintuitive. Okay, now we continue on. Yeah,
So we do 4, 3, 2.
yeah, we can combine all these guys together. And what else? In parallel, right? And then these guys in parallel, right? So out of port space. So now, would you continue it on? We have over here, we would have battery D 3, 4, 5, 6. Oh, sorry. 2, 3, 4, 5. 2, 3, 4, 5. And then C16. And then these are just you're adding them since they're in parallel. You're just adding them regularly. So this is C4 plus C35 plus C2, which is 4 plus 2 plus 2, right? That's 8 micro. C16 is just C1 plus C6 because they're in parallel. And that's equal to 3 plus 3. Yeah,
C4, 2.
yeah. Oh yeah, good. Sorry. So C4 is 2. I got your approval, and then that's tricky. Okay, 2 plus 2 plus 2. Is that good? Rock solid? Okay, yeah. So that's 6. Okay, 1 and 6. 3 plus 3 is 6.
So when they're parallel, we don't have to do their reciprocal.
Yep. And now they're in series. Good. Okay, I have to kill this, but I'm probably gonna need it later. But oh well. Okay. Final step is, remember the goal is to get one capacitor. And this one is called C1, 2, 3, 4, 5, 6. And they're in series, so they're reciprocals add. So 1, C1, 2, 3, 4, 5, 6 equals 1 over C2, 3, 4, 5 plus 1 over C1, 6, which is 1/6 over 1/6. Basically, if you combine the same capacitor and the reciprocals, you just get half out. That's like a general mathematics rule. 2/6, which is 1/3. So this is going to be 3 microns. That's the answer to this part. Good. Now, the general idea is to kind of go like this, bring it all into one. And then the next parts of the question will then you kind of go back, right? Making it go back to the original thing. So if the question never asked this, you might still have to go to this step before you can go back. Because then the question might have just asked this. Actually, this one's easy. Part B is easy. Anybody know the answer? Right? Yeah. So we're looking for Q equivalent. So the formula is C equals Q over V. So Q is C times V. So C equivalent times V. And then for 3 microfarads times 20 volts. This is, again, you don't have to use scientific notation. 3 times 20 is 60, and then it'll be coulombs, so micro. Okay, so that was a freebie. Next one. What is V1? Okay, so here's what I mean. Had the question never answered these two, you won't be able to answer this without doing these two. Okay, so that's what both, without doing eight. And how do we get V1? Oh man, I've been sharing the whole time. Okay. Oh well. But they still see this tiny little thing. Okay, those are the boards here. So those are at home. Okay, screenshot that. Okay, go back to sharing. Okay, so V1 is the voltage across C1. But we already said that it's in parallel with these two, with C6. So that means it's also the voltage across C16. Okay, that's our little strategy. So now where those phrases come in handy. Okay, in parallel, that means same voltage, different charge. Now, C16 was in series with all these guys, right? And the phrase was same charge, different voltage. Okay, so kind of give you an overview. That means the charge that resides on this entire equivalent capacitance is also the charge here, the charge here. Right? And then knowing that charge will allow you to get the voltage. Okay? So that's how you kind of go backwards. Backwards on this. So going, stop sharing. Okay, so here. These are in series. That means the equivalent charge that we just found is on the same on both of these. And knowing that equivalent charge, we can then find the voltage difference between these. Okay. So V not 1, 2, 3, 4, 5. 2, 3, 4, 5 is equal to Q equivalent over C 2, 3, 4, 5. Good. And for part B, that's 60 microcoulombs over 6 microfarads. Micros cancel. That's 10 volts. So this is 10 volts. Now, already knowing this is 10, what do you think this has to be? Yeah, because they have to both add up to 20. Okay, but let's say you didn't know that. So B16 is Q equivalent over C16. So that's 60 microcoulombs over 6 microfarads, the same. Give it 30 volts. And back to the picture, if the combination C16 is 10 and C6 and C1 are in parallel, then the voltage across C1 is 10, the same. So this means V1 is just 10. Okay. So this is like a little puzzle. It starts giving you a bunch of answers. Because the next one is what? What is the charge on C1? Well, this is super easy. If you know the voltage and the capacitance, then you know the charge. It's going to be C1 by V1. And C1 is 3 microfarads times 10 volts, which is 30 microfarads. Okay, so that one was fast and easy. Next. What is V2? Oh, V2 is way over there. But what? Oh, okay, sorry. Well, V2 is way over there, but by the same logic, V2 is in parallel to all these guys, which is in parallel to the combination, which we already said is 10 volts. That was so easy, just using words. 10 volts. So E, two is parallel to C2, 3, 4, 5. So V2 equals, and so by the way, this what you should have in your paper. Otherwise, you just say that. I know, just copy my answer that's given to you, or actually understood how you got it. F Q2. So once you know V2, you can get Q2. Q2 is just C2 and B2, 2 microfarads, and volts, 20 microfarad. Next, next is the Q3. What is charge 3? All right, think again. We know the voltage. So it's 10 volts. We know they're in series. What do we know about the charges? Same charge. It's only parallel with the same voltage. Series, different voltage, same charge. And but we're trying to find the charge. So if we can find the charge across this combination, it'll be the same charge. So let's say because C3 is series with C35, Q3 will equal Q5 will equal Q3. Okay, and Q35 is the voltage times the capacity. So this is equal to C35 times V. CV. And C35, I think I erased it. Anybody know? Tell me what C35 is. 2. Okay. 2 microfarads. And then V35 is 10 volts. So you have 20 microfarads. That's your answer. So it looks complicated, but you do it section by section. So the same formula. And then the last part, B3. And that's easy. Once you know Q3, then you get B3. So B3 equals C3 over Q3. So it's 20, no, 4 over 20. No, I have it. I am this thing. Q3 over C. 20 microfarads over 4 microfarads. And you get 5 volts. So that's how you do all of them. Now, this problem was kind of arranged very logically. Your homework might not be that logic, it might just jump to here, right? But yeah, the idea you have to go to the equivalent capacitance. Once you have that, you go back out. That's it. Right. Perfect time. I still have I'll today. At 4.
I have a question about I was trying to do this, problem before, when it comes to that one. It has something to do with like taking the potential energy, like basically conserving energy. I just don't know how to really set it up. That's what I'm doing.
Okay. So you draw the 50 microcoulomb target, one
Yeah,
at 3 and one at -3. And you release another a -15 on the y-axis.
yeah,
So it's going to be attracted,
it's
right? They'll go straight through the axis. What is it? So where is it being released? Does it say?
not the same. It tells you the kinetic energy of white or
Okay. So yeah, that's all you need. That's the initial energy. Then the final energy will be at the board. So we were to draw this. Um, and it was launched somewhere, but then it has at 4 meters, it has kinetic energy. Oh, this is what is it? -15. So it's moving along here would be at this point. So the total energy here is going to be 1/2 mv squared plus the potential energy due to these two. Okay, so it's going to be Q. Let's call it. This is 1, 2, and 3. 1 times B. No, 3. The charge 3 times V1. Plus V2.
and so would you account when you're looking for your potential energy, would you count for the 3 meters as well? Like would you have to take it from the hypotenuse?
Yeah, it's always the distance between them.
Okay.
So V1 will be finding this one, this distance,
So,
and V2 find this distance.
It's 5. 5 trying.
Yeah. So this will be 5. So you put this will be equal to KQ1 5 meters. This will be KQ2 over 5 meters. And then when the particle gets to here, that'll be E final.
Yeah.
And it's asking what's the new speed. Right? What is kinetic energy? So it's not even asking for the speed.
Yeah.
It's asking what's kinetic energy at this point. Q3, but you have different potentials then.
There's also
And so you recalculate it, it's not 5 anymore, it's gonna be 3. 3.
okay.
Yeah.
Thank you.
Yep.
So, that's one.
Bye.
A lot of like I took